Welcome. Today's notes worksheet is entitled Matrix Algebra. I guess it should be noted at this stage of the unit that we've been working with systems of equations, and we've actually been able to solve those systems of equations through three different methods. Substitution is one method, elimination is a second method, and then Cramer's rule was our third method, using determinants. Well, what we're going to do is find a fourth method to solve systems of equations using matrices. But before we kind of get into that, I think we need to take a little time and develop some of the algebra that goes into working with matrices. So that's what this lesson does represent. So let's start it out here. Just what I have on your paper is just a matrix. And just want to be clear about a couple things. A matrix is a rectangular array of numbers, essentially a table of numbers. And as you can see, it is numbers included inside a couple brackets right there. Now I'm going to go ahead and fill these pieces out first, and then just quickly come back to this idea of the brackets holding in these numbers right here. So first and foremost, just a couple buzzwords that go with working with these matrices. Elements would be the values inside the matrix, and so in this case, I've got 6. It looks like 6 elements there, the 2, the -4, the 1, the -6, the 3, and the 0. 6 different elements. Now rows, of course, you're going to think horizontally when working with these matrices, and you're going to be doing this a lot. I have 2 horizontal rows, so 1 there and 1 there. So 2 rows. Just be very clear on that piece. Columns, of course, make sure you're thinking vertically. How many vertical arrangements do I have here? I have 1 and 2 and 3. So 3 columns there. Please do make sure you see that first and foremost before we're able to continue on the rest. And you'll hear me talk a lot about the dimensions of matrices as we go through the process here. So dimensions is always rows by columns. So in this case, it's a 2 by 3 matrix right here. Now one thing to note, and I promise I'll be very quick with this, and then we'll get into some of the operations that we're going to work on, but I want to be clear about one thing, and let me go ahead and create sort of a square matrix. And so you don't have to write this necessarily on your paper. That's fine by me. But if I had this, 1, 2, 3, 4, just like that, with these brackets right here, this is just a matrix. Actually, I changed my mind. I think this would be a good idea. If you can kind of put that in place, that would be great. Just find a little spot, if you would, maybe right in here. So when we have our 2 brackets, that notation essentially tells us that that is just a table of 4 numbers, and that would be a matrix. Now here's what I want to differentiate. From the previous lesson, remember the 2 vertical bars, everybody, is something different. So this is not just a table of 4 numbers. This, with the 2 bars out on the outsides, tells us to perform a very particular operation on it. This is what is called the determinant of our 4 values. And so in the determinant, of course, we actually do the operation where we do the main diagonal minus the secondary diagonal. And of course here we get 4 minus 6, which is -2. No big deal. But I do want you to be very, very clear on this piece. We do not evaluate these numbers over here into something. This is just an arrangement of 4 values, 2 rows, 2 columns. That's a matrix. This, everybody, of course, is a little different. This is the determinant, and those 2 vertical bars separate it. So please don't write this when you mean this. All right, I'll stop with the melodrama, and let's go get into the next piece. So just some operations we're going to be dealing with here. I'm going to breeze through the addition and subtraction here just with this investigation. We're not going to do a ton with addition and subtraction, but obviously these are operations with matrices, and we should be at least aware of their existence and how they do play out. What we're going to primarily focus on is the multiplication, and that'll come on the back side. So I've done this investigation before in a more traditional class. We might have to modify it a touch in this particular case, but that's okay. All right, so addition and subtraction. Here is a matrix from a previous class, and as you can see, it's just an arrangement of 6 numbers. And if you want, well, actually, I'm going to leave it for now. But I guess what I'm going to ask you to do, we're going to call this matrix A. Put a big A out in front there, if you would, just so when I say matrix A, we know what we're talking about. And notice our table is labeled nicely. Two genders, girls and boys, so those would be the rows here. And then the three columns, left-handed, right-handed, ambidextrous. So you see how many of each type, and we've got 6 elements to make that work. Perfect. Now, if this was a traditional class, I'd probably take a poll and get the information here. What I guess I'll have to do is just use the information from a previous class that I do have on my sheet, and so we'll just fill that in and we'll call this matrix B. So go ahead and put a B out front if you would there. And so matrix B would be obviously the same titles for the rows and columns here. And here's what I do have. Let's go ahead and get this going. So this particular class that I was working with had 2 and 0, 15 and 12, 1 and 1. Okay, very nice. So as you can see, I have a matrix A, 2 rows by 3 columns, matrix B, 2 rows by 3 columns, and what I want to do is perform a couple operations on them. And again, no big deal here. Let's see what the questions ask, and hopefully it'll be pretty self-evident of how to pull this off. So letter A, how can we find the total in each category from both classes? Create a matrix to answer this question. So what if I wanted to know the total number of girls who were left-handed in both classes, the total number of boys who were right-handed in both classes? For all 6 categories, how would I be able to find the total for both classes? And I'm hoping you would agree without too much issue here that essentially I just want to add them. And I think intuitively we figured that out. And I also think intuitively we're going to know how this works. So we're going to take matrix A, which is 1, 12, 2, 3, 14, and 0. And again, nice compact way to go ahead and express that table of numbers. And I'm going to add matrix B here on top of that. And what do we get? 2, 15, and 1, and 0, 12, and 1. All right. Now, I guess theoretically I should be putting a little equals right underneath and coming up with our answer here. Unfortunately, I can't do that. I don't have room. So I'll just go ahead and put a little equals off to the side. And I'm hoping you would agree if I wanted the total number of left-handed girls, well, you know, in the first row and the first column, there's the 1, and then first row, first column, there's the left-handed girls from that class. So I really just add the corresponding elements. That's really what it's going to come down to. 1 from this class, 2 from this class, 3. 12 here, 15 here, so right-handed girls, looks like 27. Ambidextrous, ambidextrous, and again, not too bad at all. And then let's do it for the boys. So I've got 3, 26, and 1. All 6 categories perfectly labeled there according to what we had up here. So in this piece and in this piece, and notice we've got all 6 right here for the total of both classes. So you just see that is a nice, quick, easy example of how matrix addition works. Okay, let's do letter B. How can we find the differences from each category between the 2 classes? Create a matrix to answer this question. So how many more ambidextrous girls are there in the first class compared to the second class? How many more right-handed boys are there in the first class compared to the second class? For all 6 categories, I think we can pull this out by just subtracting the 2. And so that's exactly what I do right here. You'll notice subtraction works in pretty much an identical fashion to addition. I've got that piece right there for matrix A. And then I'm going to subtract the values in matrix B. So again, not too hard at all. Hoping, again, just almost intuitively that you're seeing what to do. And then we're just going ahead and writing it in a more compact mathematical way. So A minus B. Obviously, the 6 categories stay the same, everybody. So do you want to go ahead and get a 2 by 3 matrix going just off to the side there? And then, again, if I want to know how many more left-handed girls are in this class compared to this class, well, 1 minus the 2. So there's 1 less in the first class than the second class, -1. 12 minus 15. And again, I think it's time to be rather quick on this end. 3, and then 2, and then -1. So the difference is from the first class to the second class right there. And that's exactly how addition and subtraction work. I think at the bottom of your sheet you just have a little conclusion with it. Let's go ahead and get that in. and then move on to probably our more important piece, which is the multiplication. So add or subtract matrices, very simply what we want to do is add or subtract, obviously depending which it is, what we would consider the corresponding elements. Notice in each case when I combined values together, they were sitting in the same spots of their individual matrices, in the individual matrix. So add or subtract the corresponding elements, and obviously what we kind of saw there is in order to do that, everything has to correspond perfectly. So the dimensions must be the same. I'm going to go back to it for just a second there. But the dimensions must be the same. This was 2 by 3. This was 2 by 3. And so my answer is 2 by 3. If, for whatever reason, this was a 2 by 3 and maybe this was like a 2 by 2, maybe this didn't exist, then simply you cannot add them. It just would not happen. I have to have things line up perfectly. I have to have corresponding elements in each and every case. And if I don't, well, very simply, I can't do it. Okay. Well then, it's time to get into the multiplication. So this is the one we're going to be utilizing as we get back into systems of equations. So please start getting comfortable with this concept. Please understand that yes, you will have a graphing calculator to do a few different things on this particular unit and with this operation, but you will also have to be able to know how to do this with only a scientific calculator. So please follow along very carefully if you would. So I came up with a very contrived way to at least get the idea behind matrix multiplication going. It's kind of silly, but I do think it works. So we're going to just try this out. The investigation I have is dealing with a sushi restaurant. And I'll show you what I'm going to label in terms of matrices, and then we'll go from there. So here's what I do have. If you would, we're going to create a 1 by 4. So I'm going to leave a little room right in there. A 1 by 4, something like this, and the 4, 6, 5, 6. Totally arbitrary in terms of the numbers. In fact, so you're going to a sushi restaurant and you're going to order a certain number of pieces. Those would represent the numbers, and these would, up here, the columns will represent the different types. So I've got tuna, yellowtail, salmon, and eel. Keep it simple, just something like that right there. So as you can see, just a 1 by 4. So matrix dealing with the number of pieces, and everything's labeled. Okay, good to go. Now guys, what I'm going to do is place right next to that, if you would, a 4 by 1. So something like this will do. And this 4 by 1 is going to have the price of each one of these. So price, give me a little dollar symbol right there. And what were my 4? Tuna, yellowtail, salmon, eel. See if you can get that in if you would. And again, totally arbitrary. I just made this up. Let's go with the $1.75 on the tuna, 2 for the yellowtail, 2 for the salmon, and how about $2.25 on the eel? All right, so something like that will do. And we have one matrix to the left, one matrix to the right, and essentially here's what I'm after. How can we find the total bill and write your answer as a matrix? So take a moment and think of it. Think about the way I labeled the categories in each matrix. And what if I asked you to total the bill? What would you do? What operations would you perform in order to get it? Now, obviously, the bill is going to be one number, right? So interestingly enough, when it says write your answer as a matrix, it's probably just going to be a 1 by 1 matrix, which would be the total bill. So I'm going to go ahead and do this. And as a matter of fact, it is matrix multiplication. So I'm going to, as dramatically as possible, put a little multiplication symbol right there, put a little equals right there, and guys, I want just a little 1 by 1 answer. What is the bill? All right. Well, here's how I would at least do it, and then we'll grab the calculator and see if we can get an answer that works. So I've got 4 pieces of tuna. Each one costs $1.75. So in terms of the cost for the tuna, I hope you'd agree, 4 times $1.75. I have 6 pieces of yellowtail. Each one of those is $2. Total price for the yellowtail is just 6 times 2. 5 pieces of salmon, each one is $2. So total price for salmon, 5 times 2. And eel, same thing. Do you see that we work across here and match them up with these numbers going down here? 4 matches up with that. 6 matches up with that. 5 matches up with that. 6 matches up with that. If you see that, wow, we are definitely headed in the right direction with this multiplication operation, because that exactly is what matrix multiplication is all about. Okay, well, I'm going to go ahead and get that calculation going, just making sure. So let's see, I've got 4 pieces of tuna. Each one is $1.75. Got it. Now I'm going to add the cost of the yellowtail. I ordered 6. Each one was 2. And then add the cost of the salmon. I ordered 5. Each one is 2. And last but not least, I need to add the cost of the eel. I ordered 6, and each one was $2.25. Take a look at that operation before I hit enter here and see if that makes sense. So it's kind of a combination of multiplication and addition that will allow me to get the answer, and it looks like 4250 is the case. All right, one number, 4250. I'm going to just do 42.5 right in there, and that's looking good. Okay, so we check this off. How can we find the total bill? We talked about that. Write your answer as a matrix. There's your little one by one. And notice, what's great about these notes worksheets. Look what I have for you right here. It says, in this example, you performed matrix multiplication. We took a 1 by 4 matrix. That was this one. Multiplied it by a 4 by 1 matrix, which is this one. And out of it came a 1 by 1 matrix, which is this right here. And so now what we want to do is generalize when we can do matrix multiplication, what our answer will look like, and then as we do the next example or two, exactly what operations we need to perform to get our answers. So here's what I have on my paper, and I would put a little star next to this piece just so we're clear on that. And so we're going to start out with a left matrix. I'm going to call it M by R. So rows by columns. We're going to multiply it by a right matrix. I'm going to call it R by N. And when we do this, and only when we do this, I get an answer that will be M by N. And you're looking at that and you're probably not entirely sure what's going on, and that's okay. So what I'm going to do is highlight a couple things here. I hope you have enough room on your paper. I have enough room on my board, so this should work. So one thing we found in this problem up here with the sushi, and now gets extrapolated for any matrix multiplication, is this case right here. Those two values must be the same. The columns from the first and the rows from the second have to be the same. So if you can, please write that in there. Must be the same. And do you remember when we did addition and subtraction? In that case, both dimensions, they had to be the same in order for it to work. So multiplication, same deal. Sometimes it works, other times it doesn't. In order for it to work, these two numbers have to be the same. Let's go back to the sushi thing for just a sec. Here's the left matrix. Here's the right matrix. Do you see a 4 right here and a 4 right here? Those numbers have to be the same. Now these numbers right here just so happen to give you the dimensions of your answer. So dimensions of, let's put it as the product matrix. Awesome. Let's go back to the sushi problem for just a second. We did a 1 by 4 times a 4 by 1. The 4s had to be the same. And look at the outside numbers. Do you see it's a 1 and a 1? And that's exactly what just intuitively happened when we calculated. We get a 1 by 1. So notice right here, M by N. That's what you get as your answer. Okay, so let's see if we can practice it out. We're going to do 1 or 2 relatively easy ones, and then, goodness, we're going to try a longer one. So let's give it a try. I threw some strategies there on your paper just to get you thinking about it. But, honestly, you're going to need to kind of see the numbers in action for it to really click. So number one, determine the dimensions of the product matrix and set it up. That's what I do, definitely. Set it up initially. Perform the operation with the top row of the left and all of the columns of the right, and then just continue with the next row and the next row and the next row until we reach the last. Alrighty, guys. I'll show you how it works. Example 1A, left matrix, right matrix. This, everybody, is one row, see, one row, and two columns. One column, two columns. Times two rows by two columns. So we've got a 1 by 2 times a 2 by 2. So the first question, here's sort of the interesting piece about this, is can I even do this? Well, the answer is yes. If these two numbers, and this is why I always write the dimensions there first, if these two numbers are the same, you can do it. So yes, we can do it. And by the way, what will the answer look like? What type of matrix? It'll be a 1 by 2. So let's set up a 1 by 2, one row and two columns. So one row and two columns means it's going to have an answer here and an answer here. Two elements. One row, so straight across, two columns, one answer here, one answer there. All right, very nice. Now, by the way, if this was addition or subtraction, would it work? No, because remember the dimensions had to be the same. But multiplication, it does work. So it's going to seem weird to say, but think sushi when you do this. So if you remember what happened in the sushi problem, we worked across the left matrix. Remember, I matched up the numbers going across the left matrix, and I matched them up going down the right matrix. Let me just illustrate that one quick time. So remember, we went across the left matrix and matched those numbers up going down the right matrix. 4 and 1.75, 6 and 2, 5 and 2, 6 and 2.25. Those are the numbers that matched up. I multiplied there, and I added everything in between. So that's, guys, exactly what we're going to do right here. So I'm going to match up going across the left matrix, down the right matrix. So 4 matches up with the 2. So 4 times 2. Now remember, again, we want the total essentially for this row and this column. So 4 matches up with 2, and I'm going to add that to the -1 matching up with the -3. I'll go through that piece one more time very fast. Okay, across the left and work down the right. So this, 4 times 2, -1 times 3. And again, go back and visualize that sushi problem one more time so you can see that piece if you need to. Well, again, it's just arithmetic here. 4 times 2 is 8, plus -1 times -3, that's 3. 8 plus 3 is 11. So that is, and notice where it stands. It's in the first row, it's in the only row, and it's in the first column. And that's what I did here, guys. The only row with the first column. So where it goes is based on what you matched up. Row, first column. Now when I do row and second column, that would make sense to go here because this is in the only row and the second column. So let's do it. Work across the left, work down the right. 4 matches up with 5. Plus in between. -1 matches up with 0. So worked across and worked down. 4 and 5, -1 and 0. That's how it works. So you always work across the left matrix, and you always work down the right matrix. Okay, well 4 times 5 is 20, 20 plus 0, and there's your answer. So a 1 by 2, which is 11 and 20 are your elements. Okay, let's do letter B. What happens if I switch? Notice same two matrices. Let's switch them. So the 2 by 2 is on the left. times, and then the 1 by 2 is on the right, I guess I'd throw this out here. Hey everyone, can I even do this operation? Remember, the middle numbers have to be the same. Absolutely not. No go. So even though they're the exact same values, same two matrices, when I switched the order, it changed everything. Nope, wouldn't work. So that begs the question here, is matrix multiplication commutative? Commutative means that I would get the same answer no matter what the order is, and obviously I just illustrated, nope. Numerical multiplication, of course, is commutative. 4 times 3 is the same as 3 times 4. But in matrices, order does matter, absolutely. The left matrix and the right matrix. Depending on where they're switched, or where they're arranged, I should say, you're going to get an answer, or a different answer, or not at all. All right, let's try a good hard one. So this one we can do, dare I say it, and let's see what it's going to look like. I'm going to do a few operations. It would be great for you to do a few operations, and hopefully at the end of this example, it'll hopefully click. And then we'll just do a little graphing calculator stuff to wrap up this lesson. Okay, here we go. Dimensions, everybody. Look horizontal, 1, 2, 2 rows. Look vertical, 1, 2, 3 columns, 2 by 3. Looks great. I'm going to multiply that by 1, 2, 3 rows. 1, 2, 3 columns. So can I do this operation? Absolutely. Middle numbers are the same. What's it going to look like, everybody? It's going to look like a 2 by 3 matrix. So just like this, as a matter of fact. So it's going to have 2 rows and 3 columns, meaning 6 elements. Now don't do this on your paper, but I'm going to go ahead and just throw in the placeholders essentially. There are 6 elements that need to be filled in. And notice their position. Think of their position, and you might have a shot at seeing what goes together. This one is in the top row in the first column, top row second column, top row third column. This one is in the bottom row first column, bottom row second column, bottom row third column. Wherever it is, that's what I match up in these two matrices. Okay, so let's go for it. I work just at the top left, and then I go across and work my way down. You can do whatever you'd like, whatever works for you. But I'm going to go ahead and do this. This one right here was the top row, and it's in the first column, right? So that's what I'm going to match up, everybody. The top row of the left and the first column of the right. Again, think sushi. Row of the left, column of the right. One more time, just for good measure. Row of the left, column of the right. Let's do this thing. So these 3 numbers match up with these 3 numbers. If I asked you for a total bill, quote unquote, 2 would match up with 2. 4 would match up with 4. -1 would match up with -3. And we would add those values. So I'm going to do this. First row, first column. And match up the numbers. So one last time. Across the left, down the right. Sorry for being redundant, but answered many questions over the years about how this plays out, trying to be as clear as I possibly can. So these are the numbers that match up when I do exactly that piece. So first row and first column, and let's go ahead and get an answer on this. 4 and 16 and 3. 4 plus 16 plus 3 is 23. So this answer right in here, and I think it's time for me to erase this junk. So in that first row and first column is 23. Good. And then just pick another element and go get them. Remember, there was one right here, right? Top row and second column. That's exactly what I'm going to do, everybody. Top row and second column. So top row of the left matrix. 1, 2, 3, right here. Boom, boom, boom. Second column of the right matrix. Boom, boom, boom. Match them up. 3 numbers here, 3 numbers here. That's why it works. So I'm going to do first row, second column. And again, when you get better at this, you don't have to do all this. I'm just trying to cover all my bases with you. So here we go. 2 matches up with 5. 4 matches up with 8. -1 matches up with 1. Across there and down here. That's the top row, and it's the second column. So let's see what we had. 2 times 5 plus 4 times 8, and then plus -1 times 1. I think I've got that right. I have 10 and 32. That's 42 and -1. 42 and -1 make 41. If you need a calculator, of course, please use a calculator to get you going on that. I'm going to do maybe one more and then ask you to pause and do a couple on your own. I'm going to do the top row and the third column. So that's what's right here, everybody, right? Top row, third column. So here we go. Top row, third column. So first row, third column, let's get going. Come on, here we go. 2 times 1 plus, looks like 4 times 0 plus -1 times 2. Awesome. When I do that, looks like 2 plus 0 plus -2, 0. And that's how it works. And guys, do you think we just repeat second row, first column, second row, second column, second row, third column? Of course, of course, of course. If you're doing great, please do it on your own. And you don't have to sit here and listen to each and every aspect of it. But just make sure you're able to get the same answers I do, the same 6 elements. I lied. I'm going to do one more for you and then just write in the answers for the last pieces. So now I do the second row and the first column. So second row, first column, which of course goes right here. Second row, first column. 5 times 2, 8 times 4, 0 times -3. And that's it. 5 times 2, 8 times 4, and 0 times -3. And looks like we end up getting 42, and that went right in here. Bottom row, first column. Right here, bottom row, first column. Okay, whew. Let's go get the last 2, or I should say you go get the last 2. Pause for a sec, see if you can pull it off. So last row, second column, last row, third column. All right, I'm hoping you did it. If not, so be it. You'll try some on your own, but I get 89 and 5 to wrap it on up there. So I'm going to do just a little ... right here, because obviously there are 2 more to go. But you guys hopefully did that on your own, and it's looking good. Okay, it's time to just go ahead and do a little calculator work with this. So grab your graphing calculator and just a quick investigation with this. Again, I'm going to try to find a nice balance between understanding the algebra, and please, with matrix multiplication, you are required to do some of that algebra with a scientific calculator at most. And then obviously also wanting to use the graphing calculator in certain situations. So I have 3 that we're going to look at. So 1, 2, and 3 right here, A, B, and C. We won't do all of this, but I'll just kind of show you what we're after, and then we'll go from there. Alrighty. Hey guys, let's get the 3 in. So I think we've at least seen this menu before, but go to your matrix menu if you would. And we're not doing a determinant on it, but we are going over to edit, and we're going to go ahead and edit all 3. So I'm going to be hopefully quick on this. So 2 by 2, guys. Let's go ahead and get those in. 2 by 2. Hopefully you're pretty fast at getting this stuff in as well. And good. Good. Back to matrix right there. Oops. Let's go over to edit. If I'm going too fast for you, that's okay. Don't worry about it. You can always pause and get it in yourself, but I want to run this as quickly as I can for you. So I've got that piece in there. One more. I've got A and B in. Let's get C. Oops, move it over. Now do it. There we go. 2 by 2. And this is the 1, 0, 0, 1. Good one right there. All right, it's ready. And I just want you to see a couple things that emerge here. So I'm going to do A times C. Now these are all 2 by 2s, right? So I want you to think if I can do a 2 by 2 by a 2 by 2, I should get a 2 by 2 answer. So in order to do matrix multiplication, hopefully you have those in. Let's go ahead and just go to matrix, and all you're going to do is name it. It's basically pasting it. So if I want to do A times C, I just name A. Then everybody, I go right on back, and I name C. And there it is, just side by side, it's automatically multiplication. And watch what happens when I do this times this. Look what we get. Look at those numbers, 3, -1, -2, and 1. Do those numbers look familiar? Yeah, look at this. It is A, isn't it? Cool. So when I did A times C, I actually got A. Now what happens when we switch it? I told you before, matrix multiplication is not commutative, but look what happens when I do it here. And you can just take a peek. You don't have to stay with me on this. But look at what happens when I do C times A. Notice I get the same darn thing. And so in this particular case, the matrix multiplication is commutative, and also this sort of just gave me the original answer. When I multiplied A into C, it just gave me that. And C into A, it just kept A. Now it just so happens, everybody, just to get this going, when I do B times C, I end up just getting B. So this C matrix, which is exactly what I'm focused in on here, the 1, 0, 0, 1, has a particular name. And so we have it on our notes here. Matrix C is what is called the identity matrix. And could you come up with an analogy to our number system? It is very much like the number 1. When I multiply something into 1, it stays as it is. When I multiplied this matrix into that, it stayed as it is. So that identity matrix comes up a lot, in matrix algebra. Cool. Let me do just one more, and then it leads into the next notes worksheet. What if I do A times B? Watch what happens here. There's A, guys. There's B. And notice what I get. I get the identity matrix. So in this case, instead of writing a C here, I'm going to write the identity matrix. I get that piece right there. So here is the great question. Look at the relationship. How shall I say this? What is the relationship between A and B? If they multiply essentially to the identity matrix, which is really just equivalent to the number 1, what would we call these guys? Well, think about it numerically. You know, here are two numbers that multiply to 1, essentially, its identity. What would we call these? Reciprocals, yes, but something even better. Multiplicative inverses. And that's, as you can see, if you want to do a quick flip, is the title of the next notes worksheet. So we're going to be talking a lot about the inverse of a particular matrix, and that is going to enable us to get back into solving systems of equations and all that good stuff. So please just remember with the multiplication, you are required to kind of do it without the graphing calculator, and I'll kind of show you when and where you can pick up the graphing calculator to help you. All right, everyone. Thanks for listening to the lesson there. Let me know if you have questions along the way. Try the practice problems and see if you're able to pull off the operations. Thanks.